Hello, following on from my last video on the active loop, I had a question, a very interesting question. Why does the amplifier in the loop draw so much current? 150 milliamps. Seemed rather a lot for an RF preamplifier, this guy said, and there's a good reason for this, but yes, this is a spare board, by the way, which I'm going to do some tests on. And I've built RF preamplifiers before for television reception, and you know, it would be probably 10 milliamps, the amount of current that they would draw. But the original design, which I've modified here, had a current draw of around 75 milliamps, roughly half of what the modified version that I'm using does now. So it all comes down to intermodulation distortion. When I first built this a few years ago, and it was running at 75 milliamps total, with, let's say, between the two transistors about 37.5 milliamps per transistor. So I was finding that I was getting strange signals appearing where they shouldn't be, and they appeared to be a mixture of two strong local medium wave or long wave transmitters, and there's a fair few of those around here. And we've got 198 kilohertz radio 4, which is 500 kilowatts, and that's only 30 miles away. And on the same site there's 693 kilohertz, also I think at around 500 kilowatts, radio 5. And I believe those two were mixing in the amplifier and producing spurious signals, which were appearing in the 160 meter band. So I'm going to do some tests today and show you the difference between the original amplifier current and the modified one. But first of all, I have to explain the setup. Okay, so up here we've got two RF signal generators. Got my old Marconi 2022, yeah, that's on exactly 10 megahertz. And the other one, more modern one over there, is also, well, it's actually on 10.001 kilohertz, megahertz I mean, and so it's 1 kilohertz difference between the two generators. Although in practice you wouldn't get two strong stations that close together, but it makes more sense for this test. And anyway, the outputs of those two generators I want to combine into a single signal. So I've got here a homemade splitter or combiner. The two generators come in on those two ports and you get the output signal on there, and it can be used just as well as a splitter or a combiner, but it's got frequency limitations. That's why I'm doing this test at 10 megahertz. It's more really intended to be used at VHF frequencies when I built it, but it does work at 10 megahertz fine, and it's got roughly 3 to 4 dBs loss between the two ports to the output, either port to the output. So I've now got a single output, and if we look at that on the spectrum analyzer, which I've got set up to have a center frequency roughly 10 megahertz, but you know, whatever. And it's also got a span. What's the span on this at the moment? It's a 10 kilohertz span at the moment, so that's Okay, as you can see, we've got the two signals from the two generators, and I've had to adjust the generators for the loss in the combiner to get a minus 30 dBm signal on each generator, and it looks fairly clean, the spectrum, apart from all this crap. But this is the older signal generator, which has got a lot worse phase noise than the more modern generator, because of the synthesizer's not, it's basically a 30-year difference in technology in the synthesizer. But you get the idea. We've got two signals now. Now we can connect to the amplifier, and at the moment there's no problems, there's no spurious, although if I increase the span we probably would see the harmonics of these two generators. But anyway, this is an unbalanced signal coming out of that combiner, and my loop amplifier is a balanced input. So what I have to do is convert the unbalanced signal, which is coming in there into this box, into a balanced signal, and one of the wires has fallen off. And this is basically a balun. It just happens to be a 4-to-1 balun. I mean, I don't know if it's important in this test whether it's 4-to-1, 1-to-1 or whatever. I just need a balanced output from an unbalanced. And although this is a balun, I suppose in this case you call it an unbell, because it's unbell, yeah, because it's converting unbalanced to balanced. So now what we're going to do is we're going to set up the amplifier here. And what I've done with this circuit board is I've disconnected pointer. You've got your biasing resistors here for the transistors, R4 and R5, and they've been optimized in this circuit to give you 150 milliamps or 75 milliamps in each transistor. So what I've done is I've lifted the connection there on each resistor, join those together, and I'm feeding that point from an external voltage source, so I can vary the voltage on those biasing resistors and change the current through the transistors. And at the moment I've got it set up so that it's the total current draw is 75 milliamps according to the original design. So now I'll just reconnect everything. We'll go back to the spectrum analyzer to see what it looks like. Okay, so I'm feeding in the bias voltage here, and it's the moment it's 4 volts, and we can look at that if we really want to. That's the entire consumption of the amplifier, 75 milliamps, 12 volts. And that's the bias voltage, and it's drawing no current whatsoever because it's going through some fairly high impedance, well, fairly high resistance to the base of the transistor. Let's go over to the spectrum analyzer. I think that's fairly good. So now what we can see is we've got the two main signals still, and if I look at the peak, it's actually minus 1 dBm. So the amplifier is amplifying by 30 dB at 10 megahertz. When you consider all the losses in the balun and the whatever, it's got a fair deal gain at 10 megahertz. But anyway, what we've got now is we've got spurious signals being generated, and I'm not an expert on intermodulation, but I think they're the result of the harmonics of these, adding and subtracting from the fundamentals, and you get, I think these are called third order intermodulation products. Then the next one is called a fifth order. You can see a third order, fifth order, and that's basically how it works, but I'm not an absolute expert on all this stuff. But anyway, what we've got now is we've got two unwanted products, which will be, if I put it onto the marker, I do delta. So now I've got, when I change this, we'll get a difference in frequency between that marker and the other one. So I go to this one down here. That'd be exactly 1 kilohertz away, and if I write that down, that is 32 dBs down on the fundamental, or fundamentals. So it's a fair bit of signal. If you had a strong medium wave or long wave signal, something that's 30 dBs down on that is still going to be quite audible. It's going to be quite a strong signal, in fact. And also, of course, you can go to the other one on the other side, and that one will be 2 kilohertz away, and again 32 dBs down on the fundamental. So that's what it looks like with drawing 75 milliamps, and that was the problem I was having originally. So if I now adjust a few things and I change the current or the bias, so I'm drawing 150 milliamps, which I will do now. So that's drawing 146 milliamps. So that's near enough anyway. So that's now gone down by 10 dB to minus 42. If I maybe just do that, just make sure about this. Okay. Marker delta. Yeah, it's 42 dBs down. I didn't expect it to be better than that, but it's still an improvement just by increasing the current draw in the amplifier, because you're making the amplifier more linear effectively by driving it harder. So that's improved it by 10 dB. But if I do something else and we look at it with an even lower current, and right, I've adjusted the bias now, and the amplifier is only drawing 27 milliamps, and of course the gain has gone down considerably. It's minus 14, 16 dB gain, something like that anyway. So if I now do a check on that one, that's gone down to 28 dBs roughly. So from these spurious signals, originally being down at minus 42 dBs down on the fundamental, with a lot lower current draw, they're now only minus 28 dBs down. So in other words, all these distortion products have increased considerably. I'll just take it up to about 50 milliamps. That's drawing 50 milliamps now, and the gain's gone up considerably. It's more like it used to be. So peak on that one, and so with 50 milliamps current draw on the amplifier, the intermodulation products, or the worst ones anyway, are only minus 26 dB down, and 26, 36, 37, 38, 39, 40, so that's 16 dBs worse than when it was drawing 150 milliamps. And I mean, ideally you could probably drive it even harder and draw even more current, but of course the circuit wouldn't cope very well with that. The transistors would probably blow up. But it's interesting even so to see how the difference in the biasing and how hard you turn those transistors on affects the distortion products they generate. I'll go back to 150. And then we're back down to minus 43 dBs down. So there you go. That's basically the reason I'm drawing so much current. 150 milliamps. Actually it's gone up to 166, but never mind. Okay, well I hope that's answered the question fairly well. Bye for now. Okay, before I finish, I thought it'd be interesting to look at the frequency response of this amplifier. Of course I'm not just doing the frequency response of the amplifier, you've got to consider the balun in the equation, and that's going to throw up all sorts of weird results. But I doubt this goes down extremely low in frequency. And my system over here, I'm using the tracking generator output as a signal that goes into the balun, and the tracking generator I don't think starts below 100 kilohertz, so in other words it will only output a signal at 100 kilohertz up to the 2.1 gigahertz top frequency of the spectrum analyzer. So we've got basically a swept signal which tracks the spectrum analyzer, and I've had to put 10 dBs of extra attenuation in because the lowest I can get out of here is minus 20 dBm, so I've got minus 30 coming out, and I've normalized the whole system so that I can now measure the gain at various frequencies. And at the moment the marker is set to 100 kilohertz, so it's saying minus 1 dB. I think that's more down to the balun than anything. But if I move the marker up to 859 kilohertz, you see we've got enormous gain, 33 dBs of gain. Taking into account the balun and the amplifier combined. So, I mean, I primarily use it on, say, 1.6 1.8 megahertz, top band 160 meters, 32 dBs of gain there, and 80 meters, 31 dBs gain, and we can go all the way up, and it's 10 megahertz, 27 dBs of gain, and 20 megahertz, 22 dBs of gain. Top end of shortwave, 16 dBs of gain at 30 megahertz, and I think it still works fairly well up to about 50 megahertz. So I have heard 50 megahertz signals on it. At 50 megahertz it's got 12 dBs of gain, because it's got to overcome the signal loss in the coax at those frequencies, which will be considerable with RG58, 150 feet of it. But you get the idea anyway. So it's got quite a wide bandwidth, the amplifier. It's probably more limited by the balun than the actual loop amplifier. So there you go, final end of the video. Bye for now.